Hi, and welcome to the OpenSAT Maintenance App Group Overview. This app group only contains two NASA open source apps, Memory Management and Memory Dwell, because their sole purpose is maintenance. In practice, on-orbit maintenance, or more accurately, sustaining engineering, involves several apps and some key features of the core flight executive. This video will step through a demo that highlights features of Memory Management and Memory Dwell, and future videos will address the more broad topic of sustaining engineering.
Let's look at the demo context. First, we have the Memory Manager app, and it provides commands for directly reading from memory and writing to memory. In this demo, we'll be using the following Memory Manager commands. We're going to peek memory locations, which means read them, and the result will be put in an event message. We're going to poke memory locations, which means write to them. We're going to dump memory to an event, which is a series of memory locations, dump memory to a file, load memory from a file, and fill memory with a pattern that's specified in the command. On the output side, we have the telemetry housekeeping packet for Memory Manager, and then we have the event messages that contain the data. For input and output, we have the memory load and dump files. Memory Dwell is an app that creates telemetry packets based on packet definitions contained in the Memory Dwell table. These packet definitions specify the memory addresses to be read and the size of the data item being read. The following commands are used in the demo. We're going to jam the dwell table, which means we're going to use a command to load an entry in the dwell table as opposed to loading the whole dwell table. We're going to set the dwell table signature, and this is just a text description of what's being monitored by the memory dwell. And then finally, we'll start the dwell. On the output side, memory dwell has its housekeeping packet, and it also has the dwell packet. In this demo, Memory Manager will be used to read and write to an area of memory that will be monitored and telemetred by Memory Dwell. The area is actually in Memory Manager's global data structure, and the next slide will show why it's a safe place to use. Here's Memory Manager's global data structure. The type def in mm_app.h defines the data structure, and its name is mm_appdata_t. In mm_app.c, the global data gets declared, and its name is mm_appdata, and this is the symbol that we'll be using in the demo. I manually counted the number of bytes for an offset into the load buffer array, and this is a safe place to manipulate. I also chose 256 because it's 100 in a hexadecimal, and it keeps the math simple. I have OSK's main window showing here, and I already have the CFS running in the terminal window down here. I'm going to open up the Maintenance App Group window, and under Learning Resources, I'm going to select the Memory Management Memory Dwell demo script. And when I launch that, that's going to start the Cosmos script runner, and I'm going to go ahead and hit Start, and it's going to do some setup, and during this setup, it's going to bring up two windows, and it's also going to stop the Health and Safety app, and that app prints out dots in the terminal window, so they're kind of confusing with the messages. And here are the two windows that brought up. The first one is the Memory Dwell packet screen, and this is the packet that's defined by the Memory Dwell table. And in our demo, we're going to have 4 16 bytes being manipulated, and they're going to be 4 32-bit words. And then over here on the right is a Memory Management summary screen, and this is basically a combination of some Memory Dwell and Memory Management features. And mostly we'll be looking over at the memory management status. And we don't have to worry about the file transfer at the bottom because it'll just be happening without having to analyze that. And before we hit go on the demo, I'd also like to scroll up and look at some constants we have defined. So the symbol is the Memory Management App Global Data, and there's 4 offsets, and that's at 256, and then at 260, 264, and 268. And the only other thing that's noteworthy, right, there's going to be a pattern written at some time that's A0. Okay, so let's go ahead and hit go. And the first thing that's going to happen, I just did a Memory Manager symbol lookup. So it looked up Memory Management App Data, and here's the address. And if we notice at the end, it ends in 240. So this is the beginning of the global data structure. Now, and remember, we're going to be adding 100 to it, so we should see 340 as our base address when we start manipulating the buffer that we're working with. So these next 4 commands jam the dwell table with an entry, and if you notice, they say a field length of 4. So the dwell table is treating these as 32-bit words, and that's important because I'm on a little endian machine, And when the memory dumps happen as an array of bytes, we'll see those displayed in little Indian order. So right now, now the dwell table's been jammed, and the next day, and we set the signature, but we haven't started the dwell, so we're still seeing the dwell packet as idle. When I hit go, it's going to start dwell, and here we see the dwell table starting to populate. So the sequence count's going up. We have the signature, memory management demo. The byte count is 16, and there's 4 addresses. And so here the 4 rows are all zeros because we're coming up from an initialization state. Next, we're going to do some pokes and peeks and dumps and events to look at the data and play with it. So the first thing that's going to happen is it's issuing 4 poke commands with a data size of 32 bits. And basically, these are just a counting sequence. So it's going to count up from 1 to 16 hexadecimal into our 16-byte location. And next, we're going to do 3 peaks, and it's going to look at it at different sizes. So we're going to peek at the offset of those 4-byte offsets. So first one's going to be an 8-bit, then a 16-bit, and then a 32-bit. So we'll see these event messages come up. And at the 8 bits, it's the 4, which is in the upper right corner. Then the 16-bit is the 7 and 8. And then the 32-bit is the 3rd row, complete row. And those are all in preserved Indian. Next, we're going to do a memory dump in an event. And this is treated like just a memory dump from on a starting address of 8 bytes. So when I hit go, it's from the, if you notice the bottom, 340 address. And so it picked these first 2 rows up. But we see that they come out as 4321 8765. Next, it's going to dump memory to a file, transfer it to the ground, and display it. So we're going to dump the whole 16-byte buffer, and it's going to bring up the tool to launch the table manager. Next, we're going to open the file, the dump file from the server, and it's memory management dump demo. Then we're going to use the text file that tells Cosmos how to interpret the dump file. So we see that we dumped 16 bytes, and once again we'll see that it's in little Indian order, but it goes through the whole 16-byte array. So there's the memory dump. We're going to close this down, and now we're going to fill the middle 2 rows with a pattern, the A pattern. So I just issued a command to do the fill, and then now notice it started at 344. And so we see the middle 2 rows turn to A's. Now the next step is going to take the memory dump file, which is going to reload the 16 bytes back that were dumped. And then we'll see these A's go back to the initial incrementing pattern. So I'm going to hit go again. And it just said load memory from the file. And if we go over the memory dwell, we see that it is restored. So this concludes the Maintenance Dump app intro and demo. I hope you found it helpful, and additional videos will go into more detail for Memory Manager and Memory Dwell. Thanks for tuning in.